So look at this definition with dot product. One of the neat things about it is we know that I and j are perpendicular, so I dot j is equal to 0, the number 0, because they're perpendicular. In general, for any vectors, u dot v equals 0 if and only if u is perpendicular to v, right? They're at right angles. Once again, I'm assuming that neither of these are the 0 vector. In general, the 0 vector will not show up much in this class. You should always be careful. It's just like safe sex, kids. Always be careful with dividing by 0. Okay, so what's next in the line here? Oh, another thing. So we have an equality, an inequality law. Remember, so this is a version of Schwarz's inequality, which I don't remember if you guys know this or not yet at this time. But for absolute values, you probably know this for absolute values. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This is the most basic Schwarz inequality. I don't know, you know what? I've taught algebra and pre-calculus a bunch. I don't think I ever really went into a lot of detail with this. So, but this is great to know. For vectors, it is the case that the absolute value of u dot v is less than or equal to the norm of u times the norm of v. And why should that be? Well, what is this? This is the norm of u times the norm of v cosine theta absolute value, right? Cosine theta, the biggest it can be is 1, and the smallest is -1, but this absolute value is stripping this off. This is the same as the absolute value of the norm of u times the times the norm of v, absolute value, times the absolute value of cosine theta. And the reason is because you can do this. The absolute value of a times b is the same as the absolute value of a times the absolute value of b. But the absolute value of cosine theta is less than or equal to 1. So this is less than or equal to 1 times. These norms are always positive. So I can get rid of the absolute value sign. I don't need to multiply by 1. So this is less than or equal to the norm of u times the norm of v. Right? And we started here. So we started here, and we went down here, we went here. So this, basically we showed this is less than or equal to this, which was the thinner. It'd be good if you could think about it like that. You're not being asked to prove things at this point very much. Actually, in my exam that I'm giving out that's coming up, I am going to ask you to not prove something, but essentially figure out something that is theoretical, and if it could be considered a proof. You get a numerical answer, but it's similar. I hope my students find it very exciting. Now I want to clarify some issues that we brought up. Remember, we were talking about the ith component and whatnot. Well, I want to talk about this notion of projection and component really closely. By definition, the projection of u on v is going to be, well, so first let me draw the picture. So here is u, here is v, here's some angle between them, right? What they're talking about, the projection of u on v, is they want to know, now this doesn't have to be, actually let me pull it out of the plane. I want to make this completely generic. Let's do this. Suppose we have this and this. Okay. Here is u, and this is v. This is a better drawing for this. Here's this theta. What they want to know is how much of u lies in the v direction. Okay, so really what they're asking for is if there's a sun here, right, and it's shining down, how much of the shadow falls? In the way, that's why it's called projection, right? And so it should be relatively easy to see that this is this from this picture. How do we figure out what that is? The most important thing to realize about the definition is that this is a vector, right? The component is the scalar of this vector. So here's what they want. Think about this. What's the length here? It is the norm of u. So what is this? The norm of u times cosine of theta is exactly going to be what this length is, right? But this is a number. I want to multiply it by a vector in the direction of v, and I'm going to use a unit vector, right, in the direction of v, which we know is v divided by its norm, and here's why. Here's why this makes sense. What if this, in fact, were like this? Then projecting it down, I'd run out of v. So this is the deal. The definition of this, I remember when I first saw this, the definition of this is u dot v over the norm of v squared times, I'll put it like this, the vector v. This is a number, this is v, but look what happens. This is what I said. This is the magnitude of this length here. This is the unit vector. Let's look and see what this is. So u dot v is the norm of u times the norm of v times cosine theta. Then we divide it by the norm of v squared times v, right? This is I'm just following the definition of right here. We can do a little algebraic moving around. I got v on top, norm of v on top. I got 2 on the bottom. This is the same as the norm of u. Cancel 1 on the top, cancel 1 on the bottom. Norm of v cosine theta times v bar, or v arrow. This is a vector still. I'm going to pull this out. This is the same as the norm of u times cosine theta times the vector v divided by its own norm. Look at what we got. This is a unit vector in the direction of v. This is the scalar quantity, how powerful it's hitting down there. This is all. I remember when back in the day, I looked at that and I went, what is that? I don't know what that is, and it's making me uncomfortable. Don't worry about it. It's just like if the sun is here and it's shining down on this setup, what kind of shadow would it lie? That, and remember that it's a vector, so you got to multiply it by the unit vector in that general direction. Okay, so next you're going to have this other thing called the component of u on v, all right? And the component part is just this, okay? It's just the scalar. And that's what we were trying to do before when I was saying it's the ith component, or the I component. It's the number you multiply times I. And I'm going to give you the definition that they give in the book for this, and I'm going to prove that it's the same thing. And then I'll give you guys some, and I'm not following my notes again, as usual. Where's the, okay. So the component of u on v is given by, oh, I already know this. It's u dot v, the norm of v. Let's just see what this is. U dot v is the norm of u times the norm of v times cosine theta divided by the norm of v. This cancels out. What do we get? We get u cosine theta. It's right there. Okay, so the component of u on v is the scalar in front of the unit vector in the general direction of v. The projection of u on v is just, I'm gonna confuse your words now. It's the actual vector that's going out. It's the projection on the vector in its full vector form. It's the number, it's the component times the unit vector. These are pretty important to know the distinction. If you can understand that this is a number and this is a vector, and how they're related, you're doing really, really well.